Hello, everyone. Just one quick bit of housekeeping. We will be meeting in San Francisco December 5th through 7th for Vision Weekend. Some of you are already on board. But if not, we have a whole host of amazing neurotech speakers, along with longevity, computation, nanomachines, etc. So if you're not, we would love to invite you to join us. With that being said, we're so excited to have Theodore Schwartz with us today. He's a professor of neurosurgery at Mount Sinai in New York City. He has over 500 articles published on neurosurgery, and his book, Gray Matter, was chosen by The Economist as one of the best books of 2024. So with that being said, Theodore, thank you so much for joining us. Really looking forward to Will an AI ever replace a neurosurgeon?
Thank you so much, Lydia, and thank you, Foresight, for having me. I look forward to addressing you and having an interesting conversation. What I'd like to do today is start out with a bit of a lecture or a talk where I'm going to just present you with a vignette of a conversation, and hopefully that will open up areas for discussion. So I'd like for the moment to bring you all into the operating room. Today I'm operating on a 20-year-old woman. A few weeks ago, she was diagnosed with a benign tumor about the size of a chestnut, smack in the center of her brain. The word benign means that this is not a cancer, so there's no risk that it will spread throughout her body. But it does not make this tumor in this location any less dangerous. Without surgery, it will continue to grow. Over time, it will slowly extinguish her ability to walk, to talk, to feel, and to think, until she eventually perishes from it, just as much as if it were a malignant form of aggressive cancer. So it needs to come out. I've spent most of the morning doing what us brain surgeons call the opening. To get where I need to go, I've placed this patient in a seated position, her neck flexed, and I'm sitting behind her so I can work through the back of her head, the route I've chosen after studying her MRI scan, creating a mental map of her tumor and its relationship to the surrounding brain anatomy, and then considering 4 or 5 other possible options, each of which I had determined would carry even more risk. I knew I'd encounter landmines no matter what angle I took, some expected, some unexpected, but this approach seemed to minimize the risks and reduce the possibility of any surprises. I made a linear incision where the top of the neck meets the base of the skull, removed a small piece of bone, and opened the thick covering of her brain called the dura, to expose her cerebellum, the small hindbrain that rests just below the main part of the brain we call the cerebral cortex. I put her in the seated position so that gravity will help the cerebellum fall away from another structure called the tentorium, a thick band of fibrous tissue that forms the roof of my corridor, where I'll be spending most of the rest of my day. For the last hour, I've been carefully creeping over the top of her cerebellum, millimeter by millimeter, just to get a glimpse of her tumor. Everything in this room is specifically designed to help me do my job. I'm sitting in a special motorized chair, my arms resting on supportive armrests to minimize my tremor. I'm looking through a microscope so I can peer deep into her brain, down this very narrow, dark corridor. Now, this is not your typical high school biology microscope. The neurosurgical microscope weighs over 500 pounds. Its wheels are locked to the floor to keep it motionless, and the lens and eyepieces float weightlessly above the patient's brain, suspended in the air by a complex, multi-jointed arm, delicately balanced with a system of counterweights. I'm making slow but steady progress, and as each moment passes, I make another small but critical decision. How much pressure can I put on her cerebellum? I need to displace it downwards, just enough to expose the tumor, but if I place too much pressure on it, it could swell up and obstruct my view. So I use tactile feedback. I sense the resistance as I gently apply pressure, applying increasing amounts of pressure. It's a skill I've developed over decades of practice and thousands of operations. Then I come upon a small blood vessel that's in my way. It's stretched out vertically in front of me, from the dura above to the cerebellum below, pulled taut by a combination of gravity and the downward pressure I'm placing on her cerebellum. If I push too hard, it will tear, and blood will spill out into my narrow working corridor, obstructing my view. If I want to proceed, I'll have to sacrifice this vein by cauterizing it and cutting it. But can I do this safely? Is it critically important? If I don't remove it, there won't be enough room to get the job done. But if I take it and she has a stroke or her brain swells up, then she might suffer irreversible brain damage and will never be the same. I think to myself, I've come this far and it's a pretty small blood vessel, so maybe I can get away with it. And that's when I notice another small vein nearby, and I think to myself, again, maybe that one will take up the slack, but how can I be sure? I need to make a decision. After a moment's pause, I decide to go for it. I cauterize it, I cut it, and I wait. A few moments go by and everything seems to be okay, so I keep going. After another hour of slow, meticulous work, we finally get a glimpse of her tumor. In one hand, I'm holding a small suction that looks like a bent straw, and in the other, I'm cradling a bipolar, essentially a long tweezers that allows me to send a current between its tips, cauterizing the tissue. The tumor is brownish in color, which helps me distinguish it from the surrounding pink brain tissue, but my biggest concern at the moment is its consistency. Sometimes tumors are firm like rubber, making them much more difficult to remove, and making it a very long OR day for me. If I'm lucky, this one will be soft, and I may make it home in time for dinner. As I prod and explore the tumor with my instruments, gently nudging it this way and that, I begin to appreciate that it is in fact pretty soft. I feel the tension in my body begin to release just a little bit. I core out the tumor's center, and my suction, making movements so small that to an outside observer it looks like I'm barely moving. So far, so good. That's when I realized that a small piece of the capsule, the fibrous layer of tissue that once surrounded the core of the tumor, appears to be stuck to a nearby vein, very stuck. And this is not just any vein. The capsule is attached to what's known as the basal vein of Rosenthal, which is one of the most important veins in the brain. It's a thick pipe with an extremely delicate wall that shuttles blood from the brain's innermost core. I pause and I think, if I accidentally damage this vein, this young woman's thalamus will swell up like a grapefruit and she may never wake up. On the other hand, if I leave a piece of the capsule behind, the tumor could grow back, and in a few years we'll be right back where we started, having to remove it all over again. I ask the nurse for the microscissors, an instrument with tips the size of insects' legs. I brace my hands against my patient's skull to further reduce my natural tremor. I take a deep breath and hold it, yet another tremor-reducing trick, and advance the scissors until the tips are right up against the intersection between that last bit of tumor and the vein. As I'm about to make the cut, I stop. At that moment, I begin to consider the possible ramifications of what I'm about to do. I imagine two possible futures. In one, my patient wakes up from the operation and goes on to live a normal life, career, marriage, children. In another, she has a stroke, spends a month in the ICU, a year in rehabilitation, and the rest of her life in a wheelchair. If she survives, that is. That's when my thoughts take a turn. Why do I have to make this decision? How can I possibly make it? And how will I live with myself if something goes wrong? I wish I could say this was not a typical scenario, but it is. It's one I've faced several times a week, probably thousands of times over the last 25 years. At this moment, I'm also keenly aware of the fact that I am just a human being, well-trained for sure, but a human being nonetheless. And I'm trying to make this momentous decision, one that will have an irrevocable and profound impact on another human being's life, and there's no obvious right answer. Which means that despite all my training and all my focus and all my good intentions, I could easily make a mistake. I'm here today to let you all in on a little secret, an uncomfortable truth about neurosurgery and all of medicine really, one that we all intuitively know to be true, but which doctors don't really like to talk about, which is that despite our best of intentions and despite the length and intensity of our training, mistakes happen. I'm reminded of an episode early in my career. It happened about 4 months into my internship. At that stage, I was pretty new to the practice of medicine. I barely knew my way around the hospital, let alone the human body. Sorry about the dog. I was writing some notes at the nurse's station when an announcement rang out overhead declaring a code, which is when a patient somewhere in the hospital begins to lose consciousness, becomes unresponsive, and requires emergency assistance. Just like you see on TV, everybody runs to the patient's bedside and the senior medical doctor takes charge. My chief resident was there, thankfully, and started barking out orders. She needed to push a medication through the IV, so she asked me to run to the medication storage room to get her some sodium chloride, salt water, which comes in a small vial with a pink top, which she would use to flush in the life-saving drug. I ran out as fast as I could to get it. Now, what I want you to picture is that 30 years ago, the medication room was filled with dozens of medications, stored in small, square, open-top cardboard boxes, surrounded with torn-open cellophane wrapping, everything just lying around and easy to grab. I quickly noticed a box with several small, clear vials of fluid. I grabbed one, ran back into the room, drew up the liquid, and handed it to my chief resident, who injected the medication through an IV. The patient, who was barely conscious, looked up for a second and said the following 2 words that I'll never forget: "Oh my." At that moment, her head slumped forward. I heard a loud, continuous tone coming from her EKG machine and recognized, along with everyone else in the room, that her heart had just stopped beating. That's when I looked down at the vial in my hand and my own heart stopped as I read the words on the label written in small letters: potassium chloride. Now, unlike sodium chloride, potassium chloride, if given in high enough doses, will stop the heart. It's part of the trio of medications that makes the lethal injection given to end the lives of prisoners on death's row. As it turned out, potassium chloride at the time was stored in an identically shaped bottle as sodium chloride, in an identical cardboard box as sodium chloride, wrapped in identical cellophane wrapping, sitting right next to the bottles of sodium chloride. The only obvious difference was that the potassium chloride had a green top and the sodium chloride had a pink top, which is a subtlety lost to an intern 4 months into his training in the panicked heat of trying to save another human being's life for the first time. Now I was faced with another sort of decision: what to do. Balancing my own liability against the patient's life, I ran up to the resident, pulled her aside, and confessed to my mistake, as well as the true contents of the vial. She took it in, looked me directly in the eye, and told me never to tell anyone what I just told her. Then she turned around and saved the woman's life. It was an event of such emotional magnitude that I remember it like it happened yesterday, and it still haunts me to this day. But the patient survived, and I'm happy to report that 30 years later, hospitals no longer leave potassium chloride lying around next to identical-looking vials of sodium chloride. It's locked away in a cabinet, and the key is only available upon special request. But the point is that human beings are fallible. Mistakes happen. The behavioral economist Dan Kahneman, who writes about the various sources of noise and bias that cloud human judgment, once wrote, "Where there is judgment, there is noise." As much as we'd like to all think that neurosurgical judgment is free from noise and bias, I'm here to let you know that unfortunately this is not at all the case. Just like judges give out more guilty verdicts before lunchtime since they're hungry and want to get out of court quickly, and insurance claims adjusters provide wildly different assessments of the same damage building depending on what they ate for breakfast, so too are neurosurgeons influenced by idiosyncratic experiences unique to them and to them alone. For example, how was this tumor managed by the one person I happen to have trained with? What was the outcome the last time I did this operation? If good, I'm more likely to do it that way again. If not so good, I may be tempted to recommend against surgery, even if it's the right thing to do, or to try a different approach. How do the members of my current department think this tumor should be managed? Will they agree with my decision, or will they judge me as inept if something goes wrong? These factors are not at all universal and vary from surgeon to surgeon and from hospital to hospital. Even more unsettling is the fact that the skill level of the surgeons, just like professional tennis players or golfers, varies dramatically from the top 10% to the bottom 10%, even though they're all playing at a professional level. All of this raises a very obvious question. Why do we have to rely on human beings at all? According to Kahneman, the best way to overcome bias and noise is with automated algorithms. Many things in our lives are already automated. Might not neurosurgery be next? Put more simply, could an AI ever replace a neurosurgeon? If we think about it, AIs are already impacting the practice of medicine everywhere we look. We already rely on AIs to interpret test results, mammograms, EKGs, brain MRIs, pathology slides. If given enough examples and provided with correct answers, AIs will figure out what to look for, and their accuracy will quickly surpass that of human doctors. So couldn't an AI make a better neurosurgical decision than a human? In fact, there's already an AI designed for neurosurgery called Atlas GPT. If you give it a clinical scenario, it'll provide you with all the treatment options, determine which is the best, and then guide you through the key steps in the surgery, like the step-by-step checklist a pilot might use prior to takeoff, or the instruction manual for putting together an IKEA dresser. If we think about it, the history of brain surgery has been marked by rapid advancements and remarkable technological progress. When Harvey Cushing, the founder of modern neurosurgery, began his career in 1905, the mortality of brain surgery was 50%. Think of it. Literally half of his patients died, either on the table or soon after, from bleeding or infection. And yet he returned to the operating room time and time again, facing his own limitations, not to mention the anguish of the embittered families who had put their trust in him, with the hope that with each small adjustment, each new advancement, the outcome of his surgical interventions might just get a little bit better the next time. By the end of his career, just 30 years later, the mortality of neurosurgery was down to just 8%, partly due to the development of anesthesia and antisepsis, but mostly from the evolution of his practiced, ever-advancing, meticulous surgical skill set. Even during my own 25-year career, neurosurgery has changed dramatically. When I started, if I wanted to remove a tumor lying deep in the brain, I'd make a large C-shaped incision in the skin, detach the muscle for chewing on the side of the head, remove a piece of bone the size of a bread plate, and dissect around or sometimes even go through the brain to get to the tumor. Now I can remove the same tumor without making any incisions whatsoever, operating through the nostrils using an endoscope, a long thin telescope, as well as long specially designed instruments. As an epilepsy surgeon, I'd make an equally large skin incision and bone openings to place grids of electrodes on the brain to record seizures before removing large abnormal chunks of epileptic cortex. Now I use a robot to help guide spaghetti-thin electrodes into the brain through pinhole openings in the skull and ablate those same epileptic foci with a laser probe slipped through equally small slits in the bone. We even have the ability to implant a microchip in the brain of a paralyzed patient that records the activity of their neurons and sends the data directly into a computer, giving them the ability to surf the internet, play video games, and communicate just by thinking. So-called brain-computer interfaces, such as the Neuralink device you've probably read about. Eventually, they'll be able to drive cars, fly planes, and even control robotic body doubles or exoskeletons, allowing them to move through the world freely. So what's to say what is and isn't possible? In order to understand the role only humans can play in the process, let's go back into my OR. As I sit there in my chair, arms supported, hands braced, gazing under the microscope, my microscissors poised to make that final cut to remove that last remnant of tumor stuck to the vein, another thought runs through my mind. I think back to the first office visit when I met this young woman and her parents. We reviewed the details of the operation. I answered all of their questions. As the visit was ending, her father pulled me aside in private, looked me in the eyes and said, "Doc, I know you're supposed to be the best, but I want you to make me a promise." "Of course," I said. He continued, "Promise me you'll keep my baby safe." This was a profoundly human moment. I have 4 children of my own, including my 2 daughters, roughly the same age as his daughter. I immediately knew exactly what he meant. I understood, without him saying another word, what was on the line. Neurosurgery, like all fields of medicine, is a deeply human activity, one that creates a connection between human beings, struggling with the frailty of our shared human condition. Great surgeons don't just have great hands, they have great bedside manner. When I first told my parents I wanted to be a neurosurgeon, my mother was deeply disappointed. She thought I'd choose to become a pediatrician. She thought neurosurgeons were cold, emotionless, technicians, robots, if you will. That's just not how she saw her child. But while this may be the reputation of neurosurgery, it's far from the truth. Perhaps back in the early years of our profession, when neurosurgeons lost as many patients as they saved, emotions and human connection would have been a liability. But in the current era, the vast majority of neurosurgical operations are incredibly safe, honed over decades of small incremental improvement, which allows us to bond with our patients and let down our guard. Human connection is now very much a part of our jobs, in more ways than you might think. For example, one of the operations I perform is awake brain surgery, where we literally have to remove a brain tumor while someone is alert and speaking. It sounds terrifying, right out of a horror movie, but I assure you we do this all the time, and patients are safe and comfortable. Once the scalp, the brain's covering are anesthetized, there's nothing painful about it. The brain has no nerve endings, so you can literally touch or cut into it and the patient won't feel a thing. They won't know you're doing anything. You might wonder why we would ever want to perform such a surgery. Well, it turns out that sometimes tumors grow next to important parts of the brain, like the parts that control movement or language, our ability to speak. And the brain doesn't come with labels, so looking down on the brain, you have no idea what does what. You have to map it to figure that out, which involves touching the surface of the brain with an electrode, which briefly activates or disrupts its function in a very small area. If you touch the part of the brain that controls movement, the arm or the leg will move, depending on what part of the brain is activated. And if you touch the part that controls language, the patient will not be able to speak or won't understand what you're saying just for that brief moment. So I'll literally be operating on someone, removing their tumor while carrying on a conversation, asking them about their kids, their interests, their favorite books or music, literally anything to keep them engaged and distracted from what I'm doing. Imagine cautiously digging around in someone's brain, worried about going too deep and the possibility of robbing them of their very souls while simultaneously engaging with that same essential part of them. On the one hand, you're having a casual conversation, one you might have over a cup of coffee, and you're even trying to put their mind at ease to help them not think about what you're actually doing, while at the same time you're diffusing a bomb, trying to figure out if you should cut the red wire or the blue one. This requires an enormous amount of emotional flexibility and the requisite amount of humanity. Without it, the patient might become nervous and uncooperative, and that would place the whole operation in jeopardy, not to mention their safety. So could an AI create that type of human connection? Well, perhaps they could, like an AI psychologist. Or alternatively, perhaps there might be a role for human doctors in the operating room working alongside robotic surgeons. Couldn't an AI-powered robot perform brain surgery more safely than a human? Think about the young woman on my OR table and the decision I'm facing, and the safety of the tiny movements I'll need to make if I decide to proceed. Robots don't have to brace their hands and hold their breath to reduce their tremors. Couldn't a computer analyze the situation, make the perfect decision, and then carry it out more flawlessly than me? In theory, maybe, but in practice, this is where neurosurgery becomes something very different than assembling an IKEA dresser. The brain and the diseases that afflict it are not like pieces of furniture, which are static objects. The brain and its pathology are evolving, infinitely complex, inconstant biological organisms. Simply put, you don't know what you're up against until you get in there. And as Mike Tyson reminded us, everyone has a plan until they get punched in the face. One of my neurosurgery professors used to have a saying, surgery is a contact sport. During an average operation, I make several hundred, if not thousands, of tiny little micro-decisions, one after the other, and each one represents not a mental puzzle I need to solve, but a physical one. To understand the distinction, think of the difference between chess and Jenga. Chess is a game with very specific rules. The size of the board is predetermined. The movement of the piece is fixed. The rules of the game clear and specific. An enormous number of things can occur over the course of a match, but they unfold according to a series of well-defined and unchanging rules. The square board isn't going to suddenly morph into a trapezoid. The rook isn't going to go rogue and jump over a few pawns to ambush the queen. In this type of defined universe, it took AlphaZero, an AI program, just a few hours to teach itself to play chess well enough to become the greatest chess player the world has ever seen. But brain surgery isn't like chess. It's more like Jenga, really Jenga on steroids. It happens in 4 unpredictable dimensions with an infinite number of potential problems that you might need to solve in any one move. And critically, these problems aren't mental, they're physical. Every move presents its own little kinesthetic conundrum, which must be conceived and executed to perfection, or the whole structure will topple down. While some AI-driven robots can play Jenga, even Jenga has defined rules and unchanging geometry. For example, all the bricks are exactly the same size. There are only so many of them, and the tower is constructed in the same way every time. If you alter the consistency of the bricks, make some a bit rougher, others smooth, some slightly different shape, the robots fail miserably. Imagine if Jenga had 1 trillion pieces, each brick were a different size and consistency, and the shape and size of the tower differed every time you played. Physical puzzles like this are better performed by the human brain. Have you ever seen a video of a group of robots trying to play soccer? It's pathetic, really. A group of second-raters would kick their butts. And there's a reason for that. Solving physical problems is literally what our brains were designed to do. Think about it. Our brains evolved inside bodies whose sole purpose it is to keep us alive long enough to reproduce. To do that on an inhospitable planet, our brains had to learn how to solve a whole lot of complicated physical problems. We had to learn to avoid predators, how to find food, how to design and build homes that could shelter us from the elements. And that was just learning how not to die. To really thrive as a species, our brains needed to learn how to navigate a complicated social structure, attract a member of the opposite sex, reproduce, and ultimately create communities to protect and raise our children so they could do it all over again. Computers, on the other hand, never left the Garden of Eden. They sit inside metal boxes on their creators' desks. Sure, they're really good at solving complex problems with numerous steps and manipulating quantities that our brains find difficult to grasp, but they never learned how to use a body to solve problems because, well, they never had to. Computers don't have to find energy or shelter. They get a constant source of power from an outlet. They don't have to figure out how to get along with other computers. They don't have to learn how to adapt to survive. Bottom line, they lack what's called physical intuition. And as smart as an AI might be, in the operating room with my patient's brain exposed and the microscissors in my hand, I'm not relying on mental intelligence. I'm relying on physical intuition, which reflects DNA that evolved over eons of human evolution on this particular planet and synapses formed over decades out of trillions of physical interactions with the outside world. If you want to win at chess, ask a computer. But in the heat of battle against a tumor fragment, you want a human brain on your side. It's exactly the kind of problem we were built to solve. A neurosurgical operation is like a professional soccer game played on a field the size of a postage stamp. Robots wouldn't stand a chance. Let's go back to the OR one last time because I still have this very important decision to make. This is the moment that I ask myself the most important question that a surgeon can ask. And I think it's one that an AI or a robot will never be able to answer. If it were me or my child lying on that table, what would I want the surgeon to do? A surgical robot will never fully understand the human condition because it hasn't lived, loved, lost, or grieved. It hasn't attended a wedding, a graduation, or a funeral. It hasn't visited with the patient whose life has been destroyed by a bad decision and felt the weight of that decision every day for the rest of their lives. Brain surgery is a deeply human endeavor. It leverages the strengths of our biological brains, which were designed to anticipate and solve physical problems, as well as our sense of compassion, which compels us to take pity on a fellow human being in need and do everything in our power to restore them to good health. And that's why at the end of the day, it's up to me, a human being, to make the call. So do I make the cut and risk this young woman's future, or do I leave this tiny fleck of tumor attached to the vein? All my training has brought me to this moment, but in the end, it's my humanity that makes my decision. Like I said, I have two daughters the same age as this patient, and I think about what I would want done if one of my girls were on the table. I think about their dreams, their aspirations. I think about the life that awaits them. I feel the tears well up as I imagine walking each of them down the aisle. I look down at this shred of tumor. It's benign after all, and yeah, it might grow back in another 20 years. She might need to deal with it again someday, but she has an awful lot of living to do before that day arrives. So I stop. I announced to the room that we're closing. I had made a promise to another father, human to human, and I intended to keep it. Thank you very much.
Thank you so much.
You're welcome.
Wow, there was so much there. I really love the line that computers never left the Garden of Eden. That's really interesting. Does anyone have any questions? I wonder.
Nicola.
Oh, go for it, Nicola.
That was a lovely talk. It was really very interesting to listen to you. It was as if we're following you. I felt like one of those kids bring your kid to work day. It
Yeah,
was, it-
I do that a lot. That's what I was going for.
I loved it. I agree with you. 10 years ago, Ed Boyden tried to make a machine that will do the surgeries. And as you say, the harder part is opening the skull. That drill never came out. The automatic drill never came out. I want to play the devil's advocate in defense of AI here, though. I personally believe that Elon Musk is making an error deciding to make implants that can only be done by a robot and a human will never be able to manipulate. But isn't it interesting that the human brain that is doing those very complex brain surgeries has evolved for actions that we were doing 10,000 years ago in the cave? It never evolved to do brain surgeries, actually. That's a skill that we have because of multiple other aspects that we're able to do. And the reason for that is that rather than following an algorithm, as you mentioned in the beginning, you said AI will never have that algorithm. We're able to create a world model and implement it. And when we make all those decisions, actually what we're doing is we're evaluating statistical probabilities, and computers are very good at that. And so one can imagine that AI should one day be able to carry uh, tasks where statistical probabilities are. So when you, as a surgeon, for example, have a drilling through the bone and it starts bleeding all of a sudden, your perceived reaction is, oh, there's a small surprise here, I have to react. What do? You reach for the bone wax, right? So the responses to those multitude, the myriads of problems that arise are actually out of a small, relatively small toolbox that is has a statistical probability and can be learned. That's how every surgeon learns from their predecessors. And so humans, we learn from human communication the way we have it. AI has much better communication and ability to learn from all the surgeons. You have probably one or two mentors. AI can learn from all the surgeons. Plus, there are new technologies that are emerging. If you were in Egypt, you were doing trepanations using an arrow tip and you were drilling with it. Now we have much more advanced methods. So I'm thinking about things like focused ultrasound to remove a tumor. You can go and you don't even have to open. You can converge it and you just destroy the tumor. Focused X-rays. So is it possible that we can say brain surgery is the one human activity that we will always keep? Or should we look at this? That's where the question is. Should we look through this in a different lens and be considering the fact that as every human activity, uh, it's neurosurgery is constrained by few statistically explainable actions. And therefore, we could one day foresee an AI driven, or AI is a word for nothing nowadays, machine driven.
So you make a lot of interesting points. Thank you for raising them. I would say that there are elements of the surgery that could be better done by a robot, parts of it. So, for example, let's take the implantation of the Neuralink device. The part that the robot does better is sewing in those tiny electrodes that are so small that we really can't see them. And our tremor would be such that, we would probably damage them on the way in. The human just doesn't have the fine touch to be able to do that. But that's one element of the surgery, right? The other elements of the surgery are still done by a human being. Now, I'm sure Elon wants to replace the whole thing by a robot. But the point I'm trying to make is that there are millions and millions of decisions, and some of which I think are probabilistically driven in a way that an AI could help you make the decision. But part of the issue has to do with carrying it out, like physically carrying it out, where it involves a certain amount of haptic feedback that would be hard to integrate. Or it's a decision that's not so straightforward. For example, the probabilities of figuring out whether to take that last piece of tumor off the vein, which require having tried it numerous times in the past and having an understanding of the biology of the tumor and understanding the age of the patient and understanding, the expectations of the family, all of which have to be weighed into this decision, and having my own personal experience to weigh the meaning of those. Can all of that be reduced to probabilities where there is a right and a wrong answer in the way that a computer could come up with? I think it would be very, very difficult to put that all together. And that's just one of a million decisions that you're making during the course of an operation. And things are constantly changing. I mean, that's the other thing. It's like a battlefield where one decision triggers a cascade of events that then changes all the subsequent decisions that you have to make. Now, does each one of them have a probabilistic weight and a right and a wrong answer? Perhaps. I guess I would ask you, why is it that robots are so poor at manipulating the physical environment, right? Why is it that, you watch these videos of breakthroughs and there'll be a robot making a cup of coffee for someone, and what it's doing is it's basically pushing a button on a Keurig, like that it can do. But that, a 4-year-old child could do that, right? And so I think the lack of evolution, physical evolution on our planet, solving physical problems constantly over millennia, is an issue that is going to be very difficult for robots to develop. I'm not an expert in robotics, right? So I can't tell you I know the cutting edge of that. I just see what I see, and I see what the advances are, and I know what I have to do during surgery. So I'll turn it back to you and ask you that question. Why is it that robots are so poor at navigating the physical environment?
The problem is in the humanoid form factor. We don't have good actuators to control precisely, produce enough strength, produce enough precision, plus the batteries. But you touched a very interesting point, because currently the way AI is being trained, what is required for the labeling is to have a correct answer. It's really, that's how one evaluates whether the learning has happened, is to find the correct answer. And that's why the problem of ChatGPT giving this confident lies. When you're doing your neurosurgery and you're making multiple choices, there's not probably one single correct answer. It's the answer you choose, and you take it because that's the best optimal answer at the moment for the action that you're performing. And that's not something that we train right now in AI. I think that's a very good point.
Yeah, and whatever, and someone else would do it differently. And that would create a whole new scenario that requires a whole new set of decisions as to how to navigate it. But it's a good question, is whether it's a physical limitation or whether it's a cognitive thinking limitation. in making those physical decisions.
I had a question about that sort of goes off of that conversation. I was wondering, so you mentioned towards the end about how the robots really aren't in the world with us. They're not experiencing the physical things that we're experiencing. And I guess this is something that I've noticed about AI and sort of the competent predictions that have been made about AI is that a lot of it's based off of very cerebral things like, language and existing in this mathematical and linguistic world as opposed to a physical one. And sort of the same thing goes for AI applied to biological systems, like for predicting how cells behave and so on and so forth. There's sort of a disconnect between the bits and the atoms. And I guess my question for you would be, if there was a world where robotics was significantly more advanced, do you think that there would be sufficient experiences or rather training data for AI to become more competent at things like surgery? Or do you think that there are still things that would be difficult to train even in a world with ubiquitous robotics that highly advanced?
You phrase it in an interesting way, because I've often thought about the fact that just because you can imagine it doesn't mean it's possible, right? We can imagine things. So can I imagine a world where a robot could do neurosurgery? Of course, you can imagine it. You can imagine you can see a picture of it in your head. I can imagine it easily. But that doesn't mean that it could happen. Like, I could imagine a horse evolving with 5 heads and 12 legs. Like, you can imagine that. But like, would evolution ever create a horse with 5 heads and 12 legs? Like, the probability of that ever happening is so low that just because you can imagine it doesn't mean that it could actually happen. And
You
so
don't think that there'd be a possibility that robotics would be a strongly driven technology that could become very widespread?
I can definitely imagine it. But the question is, will we ever have a robot driven by an AI that has the same sort of physical intuition about manipulating objects in the real world that a human being has done? So, I mean, obviously, the answer is yes, it could happen, right? Because you can imagine it could learn over time, and if you gave it the right haptics and the right feedback and the right ability to manipulate the world, you can imagine it. The question is, how long would it take for that to happen? And I think it's a long time, because if you think about how long it took us to be able to develop the physical intuition to live on this planet, it's eons and eons of evolution. And so, yeah, I can imagine it. I just feel like that's just not the strength of what computers and robots were built to do. They sort of they evolved to solve different problems than the kind of decisions that we make navigating the world. And sure, it's possible, but I just think it's going to take a very long time, is how I would put it. I mean,
I actually agree that it probably will take quite a long time. I've sort of been a skeptic of some of the more dramatic AI predictions, and I think that, I come from a biological background as well, and so I see a lot of people who are saying, AI is going to solve biology in certain ways, and I think that while that may eventually happen, I think that is quite a ways further off than people are predicting. And but yeah, thank you for your perspective. I also had one other question. So we've been thinking a lot about AI as sort of on its own as a separate neurosurgeon, but during your talk, you mentioned a lot of things about sort of the human limitations. And I was wondering if you know of anything where, like the hand tremors and so on and so forth, do you know if people are trying to develop ways to mitigate that through biological interventions like neurotechnology or even just pharmaceuticals that could help improve neurosurgeons' performance?
So you'd imagine having sort of an exoskeleton, like something on your hands that physically would reduce your tremor. So you'd still move your hands, but the tremor would be reduced. I've seen exoskeletons that hold surgeons upright, so you don't have back pain when you're operating. And obviously we have Da Vinci robots that humans control, where we're controlling robotic arms that have no tremor. I could imagine if you took a beta blocker, you might have a little bit less tremor, but you might have less energy as well. I'm not aware of anything either pharmaceutically or mechanically other than these sort of exoskeletons, but the exoskeletons are more to support the surgeon and not to reduce their tremor. But I could imagine something like that, like wearing a glove that was able to sense the microtremors and dampen them, right? I could imagine that. I think that would be a fantastic development.
Interesting. Thank you. Thank you.
Yeah.
Well, I guess one more devil's advocate point would be that you mentioned one of the pioneers of brain surgery reduced his mortality during surgery from 50% to 8% over the course of his career. I wonder, it seems that if we could integrate all surgery training data into robots, then that could really improve their decision making. But I guess that's contingent on whether we can fix the robotics problem.
Yeah, I mean, again, it's that sense of imagining, putting all the knowledge of every surgeon who ever operated into one database. There's decisions that we make, and then there's actuating those decisions, right? And those are two different things. And there's some actuating of them that might be done better, like as in Elon Musk's Neuralink device, when you have to thread in threads that you can't even see, that clearly is done better by a robot than a human. But again, it comes down to this sort of myriad of tiny decisions that you have to make that are not, they are physical decisions, and then they're also emotional decisions, and they're humanistic decisions. When I have a conversation with a patient before a surgery, the patient, because you can't just say that, a robot could take into account the patient's desires, right? Because the patient has a wish. What do they want me to do? Would they want me to take that tumor out? Would they not want me to take that tumor out? The truth is the patient has no idea. They don't have the knowledge to make the decision because they haven't seen, 10,000 different operations done in different ways and what the outcome is like I have. So I sort of have to make that decision for them to some extent. And I have to make that decision also based on my lived experience, and that plays into those decisions as to what to do. It's not like you can just listen to the patient or just follow a cookbook of, in this situation, this is what you should leave tumor behind, or you should try to take the whole tumor out. It's different every single time based on how stuck that tumor is, how firm that tumor is, what that conversation was with the patient, what your own sense of your own abilities are, on what you can do and what you can't do. And all of that gets weighed into a decision that obviously our human brains are very good at making in ways that we don't fully understand. And my sense is that it'd be very difficult for an AI to be able to weigh all those things because it's almost not clear. I could barely even describe to you how the decisions are made. And there's decision after decision, along the way. It's almost hard to express in a way.
I could see that.
Yeah.
I guess
I don't know. I'm proposing this and I'm open to a conversation. If you think I should be thinking about it differently, from your perspectives, I'd love to learn from all of you as well. I don't have all the answers.
Well, there's certainly things that you see that we don't as a neurosurgeon. So it's really interesting to get your perspective on it. I guess I have one kind of personal question that I'm curious about. Why, you said that you felt pressure from your family to be a pediatrician instead of a neurosurgeon. I'm kind of wondering what led you to make that decision to be a neurosurgeon.
So it wasn't pressure. It was more that when I decided to become a neurosurgeon, my parents were shocked. That's what I chose. They just never imagined that's what I would do because they saw me as this, sensitive boy who would, I studied philosophy and literature, and they thought of neurosurgeons as sort of very cold, calculating, almost like sterile individuals who have to separate their emotions and compartmentalize them, which we do have to do often. And so that was the disappointment in my parents. The reason I chose neurosurgery was, I was a musician growing up. I loved working with my hands. And I loved the instant gratification of surgery as opposed to the medical field where you would see a patient with a problem and you would say, all right, maybe they have this, here's a differential diagnosis. Let's try this drug and see how they do a month later. Let's try this drug and let's lower it a little bit. There wasn't this sense of instantly fixing a problem. And with surgery, you see a problem, you have a solution, you go in, and 4 hours later, you're done. Like, they're fixed, and they say thank you, and there's something very rewarding about having an instant impact on the world that's very tangible. Particularly since I'd majored in philosophy in college, and you could spend hours thinking about abstract topics that don't have a right or a wrong answer. You can drive yourself crazy, and this sort of instant gratification of surgery was night and day compared to that background.
Fascinating. Well, thank you so much, Theodore. This was really a fascinating talk and a really great discussion. We'll see you all next month and hope you guys have a great rest of your day.
All right. Take care.
Bye.
Bye-bye.